Okay, that was constructive proof. And next we'll talk about non-constructive proof. And here, as the name implies, we are not going to care about the exact example or the exact value that satisfies the given statement. And we are certainly not interested in any method to find it. We don't really need to find the value that satisfies the existence, but we are just after the knowledge of the existence. So here's again the same statement: that exist irrational numbers x, y, for which x to the power y is rational. Now here's a very classical proof. Now take the number square root 2 to the power square root 2. Okay, so this number, we do not know whether it is rational or not. Okay, we do not know. If it is rational, then we are done, because square root 2 is irrational, we know that. Okay, so take x and y, both of them, to be square root 2, and this number by itself, if it is rational, is an example by itself. If it is not, if it is irrational, then raise to another power of square root 2. Now you see these two, this will give you square root 2 to the power 2, because when you multiply these two, it will give you 2. And in return, this will provide 2, which is clearly rational. Okay, so this number, if it is rational, it is an example itself. If it is not, raise it to the power square root 2, which is irrational. It will give you 2. So this number will be the example in this form. Okay, so here you see we actually do not know the exact value of x and y that satisfies the given statement. Is x square root 2 and y also square root 2, or is x the number square root to the power square root 2 and y square root 2? I don't know which one is true, because I don't know whether this number is rational or not. But I do not care, because I have just proven the existence of such a setting, x to the power y. Either x can be square root 2 and y square root 2 if this number is rational, or if this number is irrational, set this to x and this to y, and then you are done. Okay, non-constructive proof. I don't have the example itself, I don't know the exact value, but I am sure of the existence. Next one is proof by exhaustion. Now here, this is useful for settings where you have several cases. Of course, you do not want the cases to be very numerous. Therefore, for practical reasons, you would like to keep the number of cases small. And here's a good example. For all natural numbers, the number n to the power 7 minus n is divisible by 7. So this is the notation we use for divisibility, which we will actually discuss later on in this course. But for the time being, this is what the statement means. N to the power 7 minus n is divisible by 7, or 7 divides n to the power 7 minus n. Now, for this proof, we are going to actually represent any natural number n as 7 times k plus r for some k and r, obviously. Well, this is the fundamental theorem of division, and therefore I can write any integer, any natural number in this way. And of course, the remainder here can take 7 values from 0 up to 6. Okay, so I have 7 cases. Now, n to the power 7 minus n, if you factor it out, it turns out to be equal to n times n minus 1, n plus 1, n squared plus n plus 1 times n squared minus n plus 1. Okay, so you have 5 terms that make up this expression. Now, one by one, you look at the cases here for the value of r. If r is 0, then you have this factor n, and r equals 0 means n is equal to 7k, which is divisible by 7. Therefore, this number is divisible by 7. That's for r equals 0. Now I have to look at the remaining 6 cases. If r equals 1, then you have this factor here, n minus 1. Okay, if r is 1, that means n gives the remainder of 1 when divided by 7. So just take n minus 1. That will be in the form of 7k, right? Which is divisible by 7, obviously. Therefore, this number will be divisible by 7. Okay? And if r equals 2, then this number has this factor, n squared plus n plus 1. If you plug in n equals 7k plus 2, due to this case, this gives you this statement, 49k squared plus 35k plus 7, which is clearly divisible by 7. Therefore, this is also divisible by 7. And so on. You go on like this. Okay, I'm not going to read all of them, but the idea is you check case by case. But of course, the key here is you have to list out all possible cases. Okay, that's essential. If you just leave out one, your proof is incomplete and mainly incorrect. Okay, you have to list out all possible cases. Another method is combinatorial proof, and this is the last one I'm going to talk about before moving into induction. Combinatorial proofs are generally used to prove identities by showing that both sides of the equation count the same thing in different ways, which we call double counting argument. Okay? Again, here's a very simple theorem. And obviously, probably all of you know this. And the left-hand side here is n choose k, the binomial term, the binomial coefficient, and right-hand side is n choose n minus k. So this is like 8 choose 3 is equal to 8 choose 5. Now I can prove this from the definition, which we know to be n factorial divided by k factorial n minus k factorial, and both of them are equal to the same thing. But, well, that's a direct proof, and that is fine. But here, I'm just going to point out how combinatorial proofs work on this extremely simple example. Now, the left-hand side, what is the left-hand side? Now, again, we haven't talked about counting methods, but this is so essential. I'm sure all of you know this. The left-hand side is the number of possible selections of k objects out of a collection of n. Okay, just select k out of n with no order. Just select a group of k. Okay, and the right-hand side is the number of possible selections of n minus k objects, not k, but n minus k objects out of a collection of n again. But these two procedures are essentially the same. Why? Because you have n objects. Okay, n objects, and selecting k is equivalent to selecting n minus k, because when you select k of them, you leave out n minus k of them. So that's the second group you actually select. Okay, so choosing k is equivalent to choosing n minus k. Therefore, left-hand side and right-hand side are actually describing the number of ways to do the exact same thing. Therefore, they have to be equal. Okay, so essentially combinatorial proofs work like this. You show by a double counting argument that the left-hand side counts the same thing as the right-hand side, but in a different way. And we are going to see some examples on this later on. And combinatorial proofs usually work like this.